Aditya, am I audible? Hello.
Yes.
Okay. We'll just wait for a few minutes for others to join, then we'll start. Okay.
Yes, sure.
May I know one thing, Aditya, that mail was floated for this week's tutorial session to happen
Yes,
by
yes.
NPTEL? By NPTEL. Was it floated for
Yeah.
this week?
Yes.
Okay.
Yes. Yes.
Okay, I think we can start. Maybe others will join. All right. So I think you were not present in last two tutorials. You were there?
No, no. I was not present.
It's your first time, right?
Yes, yes.
Oh, okay. So what do you do, Aditya?
I'm currently working at a company, so I just wanted to have a refresher for this, so I just joined this course.
Aja, okay. So you are working currently? Okay. So you are
Yes, yes,
you have done your like bachelor's or master's or something?
yes. I have done my bachelor's and then master's.
Acha, okay, okay. So you are working in like which domain in your organization? Like related to
Not
research?
as of now. Yeah, not as of now. Related to fluid mechanics, but kind of
Okay.
performance and data analysis. Yeah.
Okay, okay. All right. And where you have done your bachelor's and master's from?
Bachelor's from IIT Roper and then master's from IIT Madras.
Okay, great. All right. There is another student, Sunil Raja. Sunil, am I audible? Hello. Sunil, are you there? I cannot hear you. Maybe you need to unmute. I think he has some internet connectivity issues, maybe. All right. So, have you watched the week 3 lectures? Aditya, have you watched?
No, not completely.
Not complete. So, any assignment you have done so far from week 0 to week 3?
Yes, 1, 0, 1, I guess. 0, 1, and 2.
Okay. All right. No problem. Okay. So,
Yeah, actually, I joined the course late, so I'm running late on this. I will catch up this week. So from next week onwards, I will be as per the course.
Okay. No problem. Okay, no problem. So my name is Varnit Kapoor, and I'm currently pursuing my PhD from IIT Delhi, and I will be taking up today's tutorial on the week 3 content. And week 1 and week 2 content has already been uploaded on YouTube, if you see. So all the Excel sheet is available where all the lecture notes and YouTube links are there if you want to check out the tutorials. And today we'll start with week 3, the finite volume method, basically. So I hope you guys have a glimpse of what finite difference and basic governing equations. So that has been covered so far. And let me share my screen just a second. So I hope my screen is visible.
Yes, it is.
So in the previous 2 weeks, like mass conservation, momentum conservation, energy conservation has been done in week 1, and further continuation was there in week 2 as well for that. And basics of finite difference method was also been discussed in the week 2. And in week 3, we will be discussing about the completely on the course track, that is CFD using the finite volume method. We will be discussing, doing some few questions, and let's start this thing. And you can stop me if you have any doubts at any point of time. Okay. And all right, all these lecture notes and videos will be available after the today's tutorial. So let me start. So finite volume method. I hope what am I writing is visible on screen, right?
Yes, it is.
All right. So, all right. So if we consider the general transport equation, and from that, if we take a you say pure diffusion equation out of it, okay, and we solve it using the pure diffusion in the steady state format, and we solve this governing equation of steady state diffusion derived from the general transport equation for any property phi. Okay? I'm not particularly saying any fixed property, any particular, and it can have any property phi. And by deleting the transient and the convective terms. So the equation which we have is for the pure diffusion steady state equation. Diffusion is pure diffusion steady state equation. So the pure diffusion steady state equation is nothing but divergence of gamma grad phi plus any source term S phi equal to 0. Okay. Divergence of grad of phi gamma times plus some source term. So we assume that gamma is constant in this scenario if we assume this. And if we try to, when we are dealing with the FDM way, then we say that it is not a conservative form. But when we are dealing with over a control volume and dealing with the finite volume technique, then it is a conservative form of the equation. So the equation, this equation which is written, and it's if we convert it into a 1D equation, 1D format of it, 1D. So that will be nothing but dou by dou x of dou by dou x, not d by dx of, if I say gamma times grad of phi, so d of phi by d of x plus some source term s of phi equal to 0 for only one dimensional case. And this is a conservative form of the equation. Conservative. Why conservative? Is because the two terms have not been splitted and they have been merged into a single derivative. Okay. If I split them and then if I see, then there will be an extra term. What do I mean from here? Is that if I split it, then it will be gamma times 2 phi by dx square plus then d phi by dx and d of gamma by dx. Then there will be an extra term here, which will create a non-conservativeness in our solution. So FDM can deal with this thing because we are dealing with a particular nodes, which I've already discussed in the previous tutorial. But in FVM, you have to integrate over the governing equation over a control volume, over the control volume. And if we consider the gamma to be constant, then we can say that this term will be 0. Okay. Yes. Okay. So now integrating, if we integrate, so a control volume integration, integrate over a control volume dV, okay, which is the key step for the finite volume method, and which distinguish your all the methods or other techniques from this finite volume technique. Okay. What do we get? We get nothing but on integration. I'm performing the integration over this equation. Integration over a control volume, divergence of tau times grad phi over a control volume dV plus integrating over control volume this source term dV. Okay. So what if we apply the Gauss divergence theorem on this part? Gauss divergence theorem on this. So what can I write by applying the Gauss divergence theorem? Is nothing but we get after applying GDT, that is Gauss divergence theorem, get the integration over a control surface, that is A, n dot gamma times grad phi over control surface dA, and this will be over the control volume S phi dV, okay, on the first term. All right. Okay. So Gauss divergence theorem says that divergence of any vector quantity with the integrating over a control volume is nothing but equal to n dot that quantity, whatever the vector quantity is, that over the control surface A. So by working with the one-dimensional steady-state diffusion equation, the approximation techniques that are needed to obtain the discretized equations will be introduced now. And then the method will be extended to 2-dimensional, 3-dimensional diffusion problems as well. So application of the method to simple 1-dimensional steady state heat transfer can be illustrated through various examples which we will deal with. But first we will cover up with the first part of the 1-dimensional steady state, and then we'll come to a numerical equation problem also. Okay. So this phi is any property, gamma is the diffusion coefficient, S is the source term. So now I'll write phi is a property, gamma is the diffusion coefficient, and S is nothing but it is a source term. Okay. So if we have a set of domain, if we have, then we will, let me make a domain first. Suppose this is your 1-dimensional domain, and there is a point A here, a point B here. Okay. So property phi at A point is constant as well as at B point is constant, if we assume that. The boundary values of the phi at points A and B are said to be constant. Let me write phi of A equal to constant and phi of B is equal to constant. Okay. So it's basically a 1-dimensional heat conduction in a rod case. 1-dimensional heat conduction in a rod. Okay. So what we will do, we will, in the first step, we are generating a grid, okay, in the finite volume method to divide the domain into discrete control volumes, So suppose we will place some nodal points in the space between A and B, and the boundaries or the faces of the control volume are positioned midway between the adjacent nodes, so that each node is surrounded by a control volume or a cell. And it is basically a common practice to set up control volumes near the edge of the domain. In such a way, you can say that physical boundaries coincide with the control volume boundaries. So what do I mean? If I divide my domain in few control volumes, it's this. Okay. And I'll take the central node points. Okay. These are your central node points, okay, of the control volume. So each of this part is a control volume. Control. And for a particular control volume, there are nodal points and there are control volume boundaries. This is a control volume completely. This is a control volume boundary. Okay. And these are the nodal points. Suppose this point is P. This is basically a nodal point. So during the point of consideration for P, this point will be the west point and this will be the east point. Okay. For that particular point, considered point in the grid. So at a nodal point, P is identified, okay, is identified by P and its neighbors in a 1-dimensional geometry. The nodes to the west and the east are identified by W and E respectively. So west side face of the control volume is referred by small w, and east side control volume face is noted by small e. So let me write. This face is nothing but small w, and this face is nothing but small e. Small. Okay. So we have understood how we have discretized. And the distance between the nodes W and P, and the distance between the nodes capital P and capital E are identified by del x WP and del XP respectively. So let me make it. I'll just shift this thing. Okay. So this is nothing but del x WP. Let me this is from P to W, capital WP. This will be capital PE. The order should be maintained, either right to left or left to right. Okay. And the distance between the faces, the two faces, nothing but Lx small we, small w, which is nothing but your domain that control volume length as well. Okay, so that is nothing but the dimension of your control volume. Delta x, delta x. And similarly, you can say for the this is a control volume width. Let me write here. Control volume width. And similarly, you can write the distance between this and this as well, and this as well. Okay, that will be del x w small w capital P and small capital P and small. So this is your grid generation. Grid generation, step one. I hope there is no doubt in understanding the grid generation part, because based on this, we will be proceeding further. All right. Now the thing is to discretize. Discretize. So key step of the finite volume, because CFD is nothing but a 4 to 5 step process if we include or exclude the post-processing part. So next step is, first part is the grid generations. Next step is discretization. 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 So Sunil, are you there? Cannot hear you. I don't know you are present or just. So you have a finite volume method. We do the integration of the governing equation over a control volume, which someone is trying to join. We are doing the integration over a control volume to yield a discretized equation at its nodal points. So for the control volume, we have the control volume which we had equation del dot, or if it's a one-dimensional, d by dx of grad of d phi by dx dv plus s phi s dv by say over the control volume. Any doubts? Anand, you have any doubt? Okay, if no doubts are there, please keep yourself on mute. So how we will discretize this part? Then after using the GDT, we will write it like this: area n dot gamma d phi by x dA plus control volume SdV. All right. So SdV, here A, if you see that A is a cross section area of that control volume phase, we can write this complete second portion is nothing as S delta V. Okay, because if we assume that V S is a source term is nothing but a constant value, not dependent of over the dimension, we can write like this as dV as delta V. The volume is integrated of that control volume. Okay. Okay. So delta V is nothing but the volume. Delta V is volume. And A is nothing but the cross-sectional area of the control volume phase. Control volume. Any doubts still here? Because now we will discretize this equation.
No.
To others? Any doubts to others? So, Anand, am I audible to you? Hello? Hello? Am I audible to anyone? Hello?
Yes, yes, you are audible.
Okay. All right. I think
I do your issue at the.
yeah, I think so. All right. Now, the portion is that we have the it's a one-dimensional thing with respect to x only. So how we can convert this integration over the surface area, okay, for both the east and west faces, because it's a one-dimensional and it is moving in only x direction. So the control volume has only west phase and the east phase. West phase and a east phase. Okay. So how I can write this thing is nothing but, so if I say that so it can be written as summation over for all the phases. Okay. The phase centered for a phase, particular phase, where F is nothing but east and west, small e and small f. I is the notation for x direction. Gamma d phi by dx dot AF for that phase plus I take a source term as S bar del V equal to okay. So evaluated at the cell centroid, because all our points west that considered point P and east point all are the centroid points of the control volume. So this S as well as this S will also be also be evaluated at the cell center. Evaluated at cell centroid. Okay. And gamma d phi by dx remains the same over the entire phase for a particular phase. Either it's a east phase or it's a west phase. That will remain constant for the entire phase. Okay. So you can write, how you can write that thing is nothing but, for the east phase, if you are writing minus the west phase, can be written like this. Gamma A d phi by dx of the east plus gamma A d phi by dx of the west. So here it was I, here it will be minus I, because with respect to point P, this phase in the positive I direction and this phase is in the negative I direction. So that is why. So you can write it as nothing but plus the source term will be, you can write it as gamma A d phi by dx east minus gamma A d phi by dx of west plus SV. Okay. So A is the cross section, delta V is the volume, S is the average value of the source over that control volume. And you can say that this states this, nothing but this equation states the diffusive flux of phi leaving the east phase minus the diffusive flux of the phi entering through the west phase, which is nothing but equal to the generation of the phi, which constitutes a balance of equation for phi over that control volume through that source terms. So in order to derive the useful forms of the discretized equations, the interface diffusion coefficient gamma and the gradient d phi by dx, which we have at east as well as west phase, are required. And from the well-established practice, you can say that the values of the property phi and the diffusion coefficients are defined and evaluated at the nodal points. So to calculate the gradients at the control volume phases, there is a requirement of approximate distribution of the properties between these points. And what we will do is that we do the linear approximation, which is nothing but a simplest way to calculate the interfacial values of the gradient. And this is called a central differencing. And if you say that in a uniformly grid, linear interpolated values at the east and the west phases are given by nothing as this gamma of the west phase, if it is not constant, will be given as interpolated value gamma at capital W, west nodal point, gamma at east nodal point by 2. Gamma of the east phase will be nothing but gamma of east phase. Gamma at this east phase will be nothing but this plus this by 2. Linear interpolation. Gamma of P, I wrote something wrong here, it would be P here. Gamma of P and gamma of east divided by 2. All right, and the diffusive terms are evaluated as this diffusive terms gamma A d phi by dx E. So gamma A d phi by dx of the east phase will not be nothing but gamma E AE, and d phi by dx will be written as phi at capital East minus phi at capital P over del x E, E. How? So this was a point P of that control volume. This was a point node E of the another control volume. So this distance was nothing but del x PE, and at this east face, face E, small e is nothing but the linear interpolation. Okay, linear interpolation for the point E, capital E minus capital P divided by that distance. If you see by this thing, if you have value at a point P, if you have value at point E, a linear interpolation will be nothing but like this, and this is your distance del x E, and this is phi at P, phi at E. So this distance will nothing but phi E minus phi P. Okay, so d phi by dx nothing but phi E minus phi P over del x. Similarly, you will write gamma A of d phi by dx of west face small w will be gamma small w A small w. Now this time it will be property at point node w, the node w here. If you have a node w here, capital W, that, and this is your west face this time. West face small w, west face. So phi p minus phi w, phi p minus phi capital W over the distance del x w p, del x w p is your distance. Already that figure has been made above. I'm making for the students who have joined late. Okay, so that they don't feel confused. Del x w p, and again your linear interpolation will be like this. So this is a property at p. Here the property will be phi w minus phi b minus phi w over del x w p. Okay. In the practical situation, the source term S may be a function of dependent variable. Okay. And in such cases, finite volume method approximation for the source term, we follow nothing but a linear form. A linear form that will be discussed by the professor in the coming lectures videos. So, but generally, if the source term may be a function of a dependent variable, if source term is a function of dependent variable, then it may this implies we follow linear form. So linear form is S del V can be written as SU plus S at point P, phi at point P, property at. So now substituting all the values in the above equation, equation number 1, if we say substituting values in equation 1. The course has mainly started from this lecture. So I request you all that you go through the lecture videos as well as be consistent with your tutorial session so that if you have any doubts, you can discuss at any point of time. After putting all these values, small EAE, I'm putting this value first, this value first in this equation. Okay. Small EAE, phi at east face minus phi at P del x PE. Then gamma W, small w, A small w, that will be phi of capital P minus phi of capital W over del x of WP plus the source term which we have written plus the source term SU plus SP SP phi P is equal to 0. This is your final diffusion equation discretized in a discretized manner. Now for all the points P, I will accumulate the terms all together. For east, I'll accumulate east node alag and west node separately. Okay, and the source term. We write it here. After rearranging, you can say that for all the values, coefficients of the node for the property phi at P will be gamma E over del X PE AE plus gamma W AW over del X WP and minus SP. This is for the coefficient nodal point P. Now for the nodal point west, all W over del X WP AW phi of W plus gamma E del X PE A small e phi of capital E plus SU constant. Okay. So now you have phi P, phi W, phi E all separated for, and it is nothing but a linear algebraic equation. Linear algebraic equation in front of you, which you have discretized or PD. Okay. So you can write these in a form like this. That is nothing but AP phi P is equal to AE AW phi W plus AE phi E plus, where these are the coefficients phi W. These are the coefficients of phi west node, east node, and the node P. Okay. So where AW is nothing but, where AW is, this is, let me write here itself. AW is the coefficient of this, that is gamma W del X WP AW, gamma W del X WP AW. Your AE is nothing but gamma EAE over delta X PE, this term, gamma E AE over delta X PE, and your AP coefficient is nothing but, you can write here, AE coefficient, nothing but, if you observe, it is sum of both minus SP. Okay, sum of both AW plus AE minus SP. If you see, this is AE, this is AW, and the remaining minus SP. Okay, minus SP. That is only I've written. So values of SP and SU can be obtained from the linear modification which we have done. And this type of discretization equation is the center to the other equation for convection diffusion and for similarly for 1D, 2D, 3D. Now the solution of the equation, this discretized algebraic equation which we have, must be set up at each of the nodal points to, or in order to solve these problems. So for the control volume that are adjacent to the boundaries, the generalized discretized equation is modified according to the control boundaries, like the phi at A and B can be given as the boundary value problems as a boundary condition. Okay, and then you can compute the values at the inner nodal points. Okay, at the inner nodal points as well. Any doubts still here? To anyone? Hello? Aditya, you are there? Have you any doubt?
Yes. No,
Yeah.
no.
No doubts? All clear? Okay. Great if it is clear. All right. Now, there is one criteria to see that the equation which we have, the generalized equation which we are having, must be followed. You can say the properties like consistency, accuracy. There are criteria for that, which has already been discussed in the lecture. If you go through that, criteria name is nothing but a Scarborough criteria, which encompasses basically two things: inequality and equality. Okay, so which you have to check. That means Scarborough criteria. Be right. We had two things in the Scarborough criteria. Scarborough criteria, where there is one thing is inequality and quality. Okay, quality and inequality. So what do I mean by this is that summation of all the neighboring points to that of the nodal point P should be less than equal to 1 for all the cells. Then only we can, as well as it should be less than 1 for one cell. Then only we can say that the convergence criteria is guaranteed. Okay, convergence criteria is guaranteed. That is summation of all the neighboring points coefficient, summation of all the coefficients of the neighboring points, that is A and B, which is nothing but AP, AW, AE over AP over AP should be less than equal to 1 for all the cells, all the control volumes, and should be less than 1 for one cell at least. 1. Okay. That is our AP should be greater than the summation of all the neighboring points. Okay. Write it just in a short way. By 2, 1, less than 1. Okay. Okay. And this will ensure that convergence criteria has been met. Our solution is converging correctly. Okay. Now, let us do one problem. Now, we have understood the solution for this. Let me give you a question. I'll give you a few minutes to solve and make the equation, and then we'll discuss. The question is like this. Consider problem of source-free heat conduction. In an insulated rod, whose ends are maintained at constant temperature of 100 degrees Celsius and 500 degrees Celsius respectively. And this is nothing but a one-dimensional problem where you need two one-dimensional problem. Which is d by dx of k of dt. This time the property phi is the temperature is equal to 0 if I say is equal to, okay. And you need to calculate steady state temperature distribution in the rod. Where you are given with thermal conductivity K is nothing but 1000 watt per meter per Kelvin, and cross sectional area A is nothing but 10 to the power of -2 meter square, 10 to the power of -2 meter square. All right, simple question. Source is also not there. You can have source, cannot have both things. Okay. This. All right. You can do this question, try it out. Let me make the figure as well. Oh no, figure is not. Figure is required. Figure. This is a point A, boundary A. And this is a boundary B. The length of the rod is nothing but 0.5 meter, 0.5 meter. And temperatures at A and B are 100. Temperature at B is 500 degrees Celsius. Okay. Simple question. Very simple question. Just zoom it out. Is it visible? The question is visible?
Yeah.
Okay, after zooming out. Okay, just try it out. Take 5 minutes and make all the equation. So So consider making equal volume control volumes, equal length control volume. So you know the length of the domain. So you know how many equal volumes can be made.
How many nodes we have to consider? Do we have any?
You see, it should be equal control volume and length is 0.5 meter. So how many nodes it should come? If I have equal control volume, should be the dimension of the each control volume should be same. So you can consider 5.1 each. 0.1, 0.1,
Yeah.
0.1.
Yeah.
Okay, done. Any doubts? Or still doing? Hello?
Yeah, I have tried.
You hadn't tried.
Yeah, I have tried. I have tried.
So were you able to
Recorded.
make up the equations?
Yeah. Yes.
So what are the equations you have made? 5 equations must be there.
Sorry.
You might have framed 5 equations. Can you tell me any of the equation after putting all the values?
Okay. Yeah. Yeah. Like last algebraic equations, right?
Yeah. Algebraic equation.
Yeah. Like 300 T1 equals to 100 T2 plus 100. So I have taken 5 nodes. So
Yes.
the second is 200 T2 equals to 100 T1 plus 100 T3.
Yes, then it's correct.
Third one is
Okay, I got it. These equations are right. So let me just print the solution. Okay, let's do the solution for it. Okay. So let us divide the length of the rod into 5 equal control volumes, first of all. Control volumes. Okay. That is, then delta x will be 0.5 divided by 5, that is 0.1 each. Okay. So we have the control volume of the rod. Let me make the figure once again. This is point A, this is point B. So 5 nodes you want. 2, 3, 4, 6, 7, 8. So last one is still not good. Oh, why it's moving upward? This. Okay. Okay. So each will be, this is 1, this is 2, this is 3, this is 4, this is 5. And this is delta x, and all the 5 delta x are there. So this will be delta x over. So grid consists of 5 nodes, and for each of the nodes 2, 3, 4, temperature values to the east and west are available if you see. So if you see for the node 2, 1 and 3 is known. For the node 3, 2 and 4 are known. For 4, 3 and 5 are known. Okay. And discretized equation of the form can again be made from the above part which we have. We have already made that. The discretized equation, general discretized equation is gamma EAE d5 by dx. I'll write like this: gamma d phi by dx into A of east minus gamma d phi by dx gamma A d phi by dx east minus gamma A d phi by dx west equal to 0 for our equation. There is no source term. But here phi is, this gamma is conductivity K and phi is dt by dx of east Ka dt by dx of west equal to 0. You can write K of A AE dt by dx for a node particular point P. Suppose this node is point P for us. Okay, if I say second node is point P, so that will be dt at east face minus dt at west face over del x, not west face, east minus nodal point P, del x PE, okay, minus kw AW dt. Why I'm writing dt? It should be t. T at T minus T at W, because if this node is P, this node will be west, this node will be capital E, this face will be small east, this face will be small west. Okay, that I'm writing the generalized form. Del x WP equal to 0. Now if I club the P terms together, a rearrangement on the rearrangement, T at point P can be written as KE AE by del x PE, and from here minus AW del x WP. Am I writing anything wrong? I think everything is right. Right? Or this will be negative. Both are negative. Because we are choosing the point P now.
Yeah, both negative.
Both are negative. Or what I can do, I can write both as positive and transpose it over toward the left side. Okay. Transpose toward the left. Okay. Equal to, for east face or for west face, let me write first. It will be TW KW AW del x WP. Similarly for the east face, KE AE over del x PE. Okay. KE over del x PE. This is again a form of, this is AP, this is AW, this is AE. So again, of equation of AP TP is equal to AW TW plus AE TE. Okay. Here AW is nothing but with AWS K A del x WP. A is nothing but, oh, alright, AW W KE AE del x E, and AP will be sum of both AW plus AE. If you see, this is sum of both. Okay, sum of these two. All right. Now, if you see, that's a uniform rod. So when we are discretizing it uniformly, each cross-sectional will be same. So AE, A best will be same as A. And similarly, conductivity of the whole rod is constant given to us. Okay. So what you can say, therefore, AE is equal to AW is equal to A, and KE is equal to KW is equal to. And these are the discretized equation for the nodal points 2, 3, 4, because you have east-west faces for all of them. These, not these, above are the discretized equation for nodal points 2, 3, 4. Since east and west face temperature values are available at these nodes. Okay. Now coming to the boundary nodes, these are the internal nodes. These are nothing but internal nodes. Coming to the boundary nodes, one and five, because they don't have, one has only the east face and 5 has only the west face. Okay, so it requires a special attention for the control volume. How you will write for the node 1? If I come to here, this was your node 1, this was your node 2, and this is boundary A. Okay, so for this, for the control volume, how we will write this expression? Can anyone tell me? Aditya, can you tell me how you will write?
Like discretize the main equation using like these two only.
These two. So for point 1, when we are dealing with the east face, you will write T2 minus T1 divided by delta X. But for the west face,
we can take A, and then instead of delta X, we can take half of it.
Half of, yes, correct. Half of delta X. So requires special attention. So the equation will be for node 1. It will be T of east face. Let me write it in that way. KE or KA dt by dx of east minus KA dt by dx of west equal to 0. So KE, or I'll write just directly KA the east phase will be T east minus T at point P by delta X minus, also I'll write here as well. I have not written one thing. KE KW is equal to K and del X WP del X PE is equal to del X. Okay, equally divided. Minus KA. Now for this node, we have nodal point P, that is 1. But we don't have the east west node. So we will consider this node only, this phase boundary only, and we will divide by half. And this is at a distance of del X by 2. Del X by 2, and this is complete. Del X. So this will be T of A by del X over 2 equal to 0 for this special reduction. Now we will recollect all the P terms. So T at P can be written as Ka by del X, and I'm transposing over lift. So both will be positive. Ka over del X by 2, that is 2 Ka, this term. Oh, this term. This term I'm talking about. So 2 will go above. 2 Ka over del X is equal to Tw with nothing but there is no Tw. So there is Ta or Te, let us take first. Te, that will be Ka by del X, and there is Ta, that is 2 Ka by del X. Okay, and there is what? There is no Tw. That is 0 times Tw. Okay, 0 times Tw. This is your node 1. All right. And if we consider there was a source term as well, then it will be linear source term SU plus SPTP. Okay. Then you would have taken link, how you would have linked the source term here at that point of time. Okay. So that can be a question, but you can think over that. Right. Now to the node 5. Node 5. If I again make a diagram, every time if you get confused, you just make a diagram. So this is node 5, this is node 4, and this is boundary B. For the node 5, west face is available, west node is available.
East is not.
But east is not available. This is east face and this is west face. Again, similar kind of thing will happen. So Ka dt by dx of east minus Ka dt by dx of west equal to 0. For the east, we will treat it like Ka T B minus T5 over del x by 2. Okay, this is your distance, del x by 2, and this is your distance, complete, del x. Okay, minus, again, west face, for the west face, west node is available. So T5, or I'll write TB in generalized term, then we will write in the later part TB minus TP, and this is TP minus T west over del x equal to 0. Okay, now the equation will be, again, if I rearrangement, TP will have 2 Ka by del x plus Ka by del x is equal to west face Ka by del x 0 time east face plus TB 2Ka by x. 2Ka by del x. All right. Is it clear?
Yeah.
Okay. So our resulting equations, 3 equations from this one, 3 equations for node 2, 3, 4. Equation 1 for node 1. This equation, this equation, this equation, and this equation. Now, if I put the values of all these things, okay, then what can we get? The equations. So I've not considered the source term so far. You can put all the values. So for node 1, the equation will be 3 Ka by delta x Tp, 3 Ka by delta x T1, because it is node 1 now, is equal to Ka by delta x T2. East face for node 1 is T2 Ka by delta x, and 2 Ka by delta x Ta. Ta is nothing but 100. 2 Ka by delta x, right? So we can put the values. 3. What is the conductivity given in the question? 1000?
1000.
Area is 10 raised to the minus 2. And delta x is 0.1. 1000 10 to the power of minus 2, 0.1. Okay. So most probably is equal to
300.
not T1. T2 1000 10 to the power of 3, 10 to the power of minus 2 by 0.1 plus 100, 2 into 10 to the power of 3, 10 to the power of minus 2, 0.1. So this will be 10 to the power of 4 into 10, 300. Correct me if I'm wrong at any point. 300 T1 is equal to 100 T2 plus 200, I guess.
Yeah.
Let it write as TA only for sake of solving. TA, 200 TA. Perfect. This is a node 1 equation. Similarly, put the values. Let us put solve node 5. Let me write 5 only first. Or we can write 2, 3, 4 first. Node 2. So our equation for node 2 was this equation. So Ka by delta x plus Ka by delta x, 2a Ka by delta x, Ka by delta x, Ka by delta x. Okay. For node 2, the equation was 2 Ka by delta x T2 is equal to Ka by delta x T1 plus Ka by delta x T3. Okay, west and east phase. So 2 into 10 to the power of 3, 10 to the power of minus 2.1 T2, okay, 10 to the power of 3, 10 to the power of minus 2.1 T1 plus 10 to the power of minus 10 to the power of 3, 10 to the power of minus 2 by 0.1 T3. That is nothing but 200 T2 equal to 100 T1 plus 100 T3. Okay. Similarly, for node 3, it will be 200 T3 on the left hand side, and west and east face are T2 plus T4, 100 T4. Similarly, for I'll write 2, 3, 4 here. 2, 3, 4. 200 T4 equal to 100. West face is T3 for 4 and 100 T5. These are the equations for node 2, 3, 4. Okay. Now node 5 was left. The node 5 equation was this one. Node 5, yes. 2K plus Ka, 3Ka by delta x, K by delta x, 2K by delta x. 3K T5 3Ka by delta x, and it was west was T4 T4 Ka by delta x, then 2K by delta x Tb. So T5 300 3 into 10 to the power of 3 10 to the power of minus 2 by 0.1 T4 10 to the power of 3 10 to the power of minus 2 by 0.1 plus Tb 2 into 10 to the power of 3 into 10 to the power of minus 2 by 0.1. That is again 300 T5 is equal to 100 T4 plus 200 Tb. Okay. Now we have 5 equations, all the 5 equations, algebraic equation. These can be made into a set of matrices, all the 5 equations. So the matrix form will be nothing but $300 for the first node equation I'm writing, 300. If anyone is confused from here, 300, 100, 2, this is a constant that will go on the left hand side, and this is will come on the left. But that will be on the right hand side, and this will be on the left hand side. 300 minus 100 there is no T3, T4, T5, T3, T4, T4. So the equation is like this: T1, all the unknowns, T3, T4, T5. And on the right side will be the boundary values, 200 TA. And there is no boundary for T2, T3, T4 are internal nodes. And again 200 TB. Okay. Now similarly for T2 equation, it will be minus for internal nodes. So T1 first, then T2 you will write, and then T3. So T1 and T3 will move on the left hand side. That will be minus 100, plus 200 and minus 100. Minus 100, plus 200, minus 100, then no T4, no T5. Similarly, for third, it will be just shift the second row, minus 100, 200, minus 100, 0, 0, 0, minus 100, 200, minus 100, and last, it is 0, 0, 0, and minus 100, 300, 0, 0, 0, minus 100, 300. So if you see, it is kind of a sparse matrix and a tridiagonal matrix as well. So most of the values are 0 of this matrix. Okay, and there are 3 diagonals which are being formed. First diagonal values, second diagonal values, third diagonal values. Okay, so you see the upper and the below diagonal values are nothing but same. Okay, what kind of matrix it is? Symmetric, asymmetric. Aditya, what kind of matrix is it?
I don't remember.
So it's symmetric about the diagonal. Okay, and it's a tridiagonal matrix, triangle at all the 3 diagonals. The values are there. Rest the matrix is 0. And this is a set of equations that yield the steady state temperature distribution of the given situation. So there are very small number of nodes, only 5 nodes are there. You can even solve these 5 equations manually as well. But when there are a lot of nodes, okay, then we require some kind of coding or numerical solution. And the iterative schemes should be used for solving those. Okay. And then you have to see that your exact solution and the numerical solution is matching or not. Okay, so iterative schemes like Gauss, elimination, Jacobi, everything has been discussed in the lecture videos by the professor in week 3. Okay, all Jacobi, Gauss versions. Any other scheme you can use, you can write the code on the MATLAB to solve this kind of equation. Okay, and because directly applying the inverse operation in the MATLAB it's a heavy computational task compared to the iterative schemes, okay, because of the order of n square, n cube, something like that. Okay, and then you have to match the exact solution with compare these all the temperatures. So when you will solve all these temperatures, you will get the temperatures like this, right here. So T1, all the nodal temperatures will come out to be, after your iterative scheme, 140 degrees Celsius, 220, 300, 380, and 460. Okay, these are the numerical solution obtained. Okay, from the now exact solution, you had a differential equation that was the differential equation in the question. If you see d by dx of k dt dx. So you integrate 2 times over that control surface, control volume, okay, and then convert to control surface using GDT. That is a finite volume procedure, or just you can do normal integration k dt dx, d by dx. You do the integration, okay, to find the exact solution of it, and you'll get a temperature distribution that will come out to be some linear distribution of the temperature. So that is nothing but it will come out like 800 x plus 100. Okay, 800 x plus 100. So put the values of x and see the distribution, and you will see then a graph will come out like this for the temperature versus the distance x. Temperature versus distance x, starting from 100, then x is 0 because it is 100. Okay, left boundary A is at 100 and boundary B is at 500. Okay, so if you see, this is your boundary A, this is your boundary B. Okay, so if you see the graph will something look like this, linear distribution for the exact solution. And when you put the value, your numerical solution should match something like this for all the 5 nodes. Okay, it should match exact versus numerical. So this line is exact solution, and this is numerical at the points. Okay. Any doubts so far to anyone, both of you? The question is solved.
No.
No doubts. So may I know, like, what is your expectation from the course? What are you thinking that why you have joined this course, Aditya? What motivated you?
I just need a refresher in CFD, and then actually I know about the professor. So my friend was in IIT Madras when he attended his lecture, so I knew about him. I just wanted to go through his course once, and then
You have done
maybe
your
towards the end.
masters
I
from
don't know how
Madras.
much. Yes. So I don't know how much coding intensive this course would be, but yeah, I wanted to ask about that, like coding assignment and all.
I'm not sure the assignment will be there for like assignment do have written that you can do the coding part of this, but it is an optional thing. Like to submit a code with the assignment is not necessary. But you can, if you have these set of equations being formed, now you just solve in the code, make some for loops. Don't write directly the matrix, because if we give 100 of points, you cannot write each and a matrix with the set of array. For each node, you cannot write each rows and points. Then you have to create for loops. And when it progresses to 2D, then definitely you cannot write like this. Then there will be three-dimensional matrices will be formed. So yeah, you can try those things with as the course progress. But yes, we have to be consistent. Like I repeatedly say, but from the lecture 1, 2, and 3, week 1, 2, 3, all the persons who have joined are different. I have not met yet any same person from the tutorial 1. So if we be consistent, if you be consistent and to the tutorials, then you can ask your doubts. You can watch the lectures, and maybe you might know the professor because you have been there at IIT Madras during your masters. So in which department you were?
I was in aerospace.
Aerospace. And bachelor's in mechanical or
mechanical.
Okay. So when did you graduated your bachelor's?
Last year. Bachelor was in 21 and then master's was in 23.
In continuation.
Yes.
Okay. And where are you currently put up for your job?
Yeah, Siemens.
Like place, which city?
Bangalore.
Okay. Okay, so now we have discussed how to solve the one-dimensional diffusion equation, and in the coming lectures there will be two-dimensional 2D diffusion equation as well, and various other schemes will be introduced. I can give you a glimpse of like what are the properties involved for convergence accuracy criteria, but those will be again discussed. They have been discussed briefly in the week 3 lectures, but definitely they will be discussed again in coming weeks. Okay, so just give me a minute. Just give me a minute. Okay. Yeah. So I was saying about that you can solve these using different iterative schemes like Gauss-Seidel, Jacobi. Okay, so what's the difference in Gauss-Seidel and Jacobi is that in Gauss-Seidel you update the cell values as soon as they are calculated. Okay, like if you calculate the value at T2, so you will take the value of T1, and when you're calculating the T3, you will take the value of T2 and T1 updated values as soon as you get. Whereas for Jacobi, you will take the old values of that nodes for the neighboring nodes will be used, and then you sweep and update the values for those things. Okay, and in the direct method, as I was saying, you cannot apply the inverse operation directly to find this because it's a computationally expensive because of there are even it's just a 1D problem. If you see there are this is an n cross n matrix which has been formed. So n cross n matrix, or if you see 5 cross 5 matrix. So that means it has to go through 5 square operations. If I give you hundreds of points or thousands of points, that will be 1,000 cross 1,000 floating points will be generated, which is a computationally expensive process for directly doing the inverse. Okay. So that is why we go through the iterative method, the iterative schemes, which has an order of just n. Okay, the number of the points, that will be the sweep until the convergence criteria is met. So convergence criteria is nothing but if you have a property phi at time t and a property phi at t plus delta t, then the difference or the norm, you can say not the difference, norm, L2 norms or something are there, which we'll discuss later on, should be less than the absolute error. So if you take that error should be 10 to the power of 9, minus 9. So the norm of the property at t plus delta t and t should be less than 10 to the power of 9. 10 to the power of 9 is very low value. Okay. So that means that the norm should be less than the error, then only the convergence will be meted. Okay. And that is only possible with the iterative methods because the order of the computational cost will be of that of n. Okay. And convergence again is met through that Scarborough criteria, okay, which is a sufficient condition. If you Scarborough criteria is met, that is if the summation of AP, A neighboring points over AP is less than equal to 1. Neighboring points meet for point node P. Neighboring points are east and west. So AW plus AE should be less than equal to AP for all the nodes and less than AP for at least one node. Okay, that was the Scarborough criteria I discussed above. Okay. Then you can say that is just a sufficient condition. You can say that yes, our convergence has been met. Okay, but people in research field take the grid convergence as another way. Like they see that for 1,000 nodes, 10,000 nodes, 50,000 nodes, every time the solution is coming same. So that is also one way for saying that our grid is converged. But from the numerical point of view, from theoretical point of view, we can say that this Scarborough criteria is a sufficient condition for this thing. Okay, and you can say for Gauss Seidel, because we can solve this using this equation. The equation just we formed using the Gaussian elimination, Gauss Seidel, Gauss elimination, whatever you want. Okay, or direct or from the indirect or direct methods. So this is of iterative methods are of order n, as I said, order n, and computational cost reduces. There is no need to store all the full matrix value. Okay. But if lot of cells are there in the domain, then this GS scheme will be slow to converge. So there are acceleration techniques as well to increase the iterative methods. So one of them is like successive over relaxation, multi-grid methods are there, which definitely will be discussed by the professor in the coming lectures. And then there is another thing that is an accuracy. So accuracy is nothing but when you expand the Taylor series expansion, which we did in the tutorial 2. Okay. So what is the order of accuracy? Basically the higher order term which you have neglected. And that is nothing but a truncation error there. Okay. The higher order term which you neglect for d5 by dx square or d5 by dx. But when you are expanding it Taylor series, we have done that thing. If you go through and check out the tutorial 2 video on the YouTube, all the links are there. So truncation error is order of delta x to the power of n, depending on what nth order of accuracy you are taking. Generally, we go with the second order accurate. Okay, and lower the higher the truncation error is there, that is higher the accuracy is there. That means there are less chances of the error in your numerical simulations. Okay, and the truncation error can be reduced by the way that you reduce the spacing dx of that. If you reduce from dx to dx by 2, then your truncation error, if you see it's a del x by del x square, order of del x square. When you reduce to del x by 2, then the truncation error reduced to 1/4, because 1 by 2 square is 1/4. Similarly, if it's nth order, it will 2 to the power of n. It will reduce, but it will never ever go to 0. It will never ever go to 0. So truncation error only gives you the relative error in the domain, whereas absolute error is not indicated directly in the numerical scheme. Okay, so it gives the relative error, and you have to see from the numerical error. That is why we plot the graph to see that how the exact solution is matching with the numerical solution here or not. So truncation error is a property of a discretization scheme. Okay, property of a discretization scheme. Always remember, because you have discretized it. Okay, accordingly. So that we have done as well. So one way is by reducing the time step or by reducing the grid spacing to reduce the truncation errors and increase the accuracies as well. And then there is another thing that is a stability. So it is used in the context of iterative methods again. So error remains the same or decrease from iteration to iteration, then we call that the method is stable method. Okay, the error is same, then time step is moving from t to t plus delta t, t plus 2 delta t. Then we say that now the solution is becoming stable for us. Okay. And there are another different kind of stability analysis, von Neumann stability analysis, coupled nonlinear equations are there, stability analysis, when there is difficult to do the stability analysis. That will be discussed by the professor in the lectures, and then we will discuss in our tutorials. And convergence criteria we have seen now. Okay, we have discussed that just right now. Okay, so this was all from my side for today's tutorial. I hope it's all clear to all of you.
Yeah.
Okay, so we can end today's tutorial, and I'll see you in the next session. All right. Bye-bye.
Okay, bye.